Hello everyone. Welcome to the series. This is the second video in our series, and today we're diving deeper into the widely cited paper, Retrieval-Augmented Generation for Knowledge-Intensive NLP Tasks, authored by researchers from Facebook AI Research, University College London, and New York University, and published in April 2021. Let's understand the problem. The knowledge of language models mainly depends on their training data. If a query is about recent information, the model can't answer. So we can say that they have a knowledge cutoff limit. And also they lack external memory access, and their knowledge base is static once trained. No updates are possible. Coming to their limitations. Standard language models suffer from hallucinations, making up facts. No source attribution, you can't verify the origin. And of course, outdated information. These limitations call for a new approach. The author proposed the RAG framework. Think of RAG as connecting a language model to external world. In our case, it's an external knowledge base. This connection enables the model to deliver accurate, verifiable responses by dynamically accessing up-to-date information. Now we will go deeper into the architectural breakdown. The RAG model works in two phases. Retrieval: it retrieves relevant docs based on query, and generation generates answers based on user query and docs retrieved. It blends parametric generation with non-parametric knowledge store. RAG variants. RAG sequence uses a single document for generating the entire output, whereas RAG token retrieves a different document at every generation step, more flexible but heavier. Now, why RAG works better? Unlike traditional language models, RAG produces factual responses, cites sources, and remains up to date. Think of RAG as a smart assistant that doesn't just rely on what it already knows, but actually looks things up before answering. Instead of depending only on its training, RAG retrieves relevant documents from an external database and generates a response using both the question and the retrieved facts. This means giving your model access to a real-time library. Now moving to the second page, the authors explain the architecture and methods using a clear, well-crafted diagram. We won't dive deep into how language models work. For now, just think of them as pre-trained predictive black boxes, trained on massive datasets to learn language patterns. They don't truly understand meaning but predict the most likely next word or token based on context. Going internally, they use layers of neural networks to model relationships between words, phrases, and concepts in a statistically grounded way. Now, let's talk about the main diagram that simplify the entire RAG framework. It includes components like the user query, query encoder, retriever, generator, and finally the knowledge source. In next section, we'll explore them one by one, with the help of clear, step-by-step illustrations to build a strong conceptual understanding. As we have seen the core limitations of standard language models. While these models are incredibly powerful, they have significant drawbacks, especially when it comes to knowledge-intensive tasks. The LLM knowledge problem. They tend to hallucinate, can't reliably provide up-to-date information, and often lack transparency in how they derive their answers. RAG architecture overview. First, a user inputs a query, for example, a question about a recent news event or a technical concept. That query is then sent into a query encoder, which transforms the raw input into a dense vector representation. Mathematically, we denote this as E sub q of x. This dense vector is then passed to the retriever, which plays a crucial role. The retriever uses a technique called maximum inner product search, or MIPS, to efficiently find the top k most relevant documents from a large, domain-specific knowledge base. This retrieval process gives us a set of top k supporting documents based on probability sampling, which we'll refer to as Z. Now comes the generation phase. A pre-trained language model, like BERT T5 or GPT, takes both the original query X and the retrieved documents Z as input and generates a final answer y. This generation is modeled as p sub theta of y given x and z, where theta represents the parameters of the generator. The result is a well-informed, grounded answer, not based solely on what the model remembers, but enriched by real, retrieved facts. This process can be represented mathematically by the equation shown on screen. RAG variance and training. Moving on to RAG variance, there are two main approaches: RAG sequence same docs for entire sequence and RAG token different docs per token. Both of these architectures can be trained end-to-end, and that training happens in 4 main steps, which are listed on the screen. RAG optimizes a log likelihood loss, and the key idea is to jointly train both the retriever and generator, allowing the model to learn what to say, and also where to find the relevant knowledge. RAG advantages and applications. Key advantages of RAG: updated non-parametric knowledge, source attribution and citations for verifiability, accuracy, cost efficiency, and the ability to access external data. And when it comes to real-world impact, RAG's applications are both powerful and diverse. From question-answering systems and virtual assistants to legal document analysis, RAG is proving to be a game-changer. As you can see, RAG brings together language models, knowledge, search, and memory into a single intelligent framework, making it one of the most promising architectures in the evolving landscape of AI. In this part of the paper, the authors focus on the experimental validation of the RAG framework. They have tested RAG across a diverse set of tasks to evaluate how well it performs in different real-world settings. This experiment spanned 4 key domains: open domain question answering, abstractive question answering, Jeopardy-style question generation, and fact verification. In every task, RAG outperformed baseline models with more accurate and knowledge-grounded results. This is the official HuggingFace Repo shared by the authors. Containing other details and resources on RAG, you can find the link in the description. And here are some of key details of the training setup and the datasets used from the index of paper. Apart from this, there is a key drawback in RAG. It is termed as the retrieval collapse, where the retriever keeps returning the same document regardless of the input, making RAG act like a regular language model. That is it for this breakdown of RAG. In the next video, we will code RAG architecture from the scratch in Python. Thank you for watching.